Hello, my name is Anthony Bonafide. I am a principal software engineer with Dell Technologies, and today I'm going to talk to you about EdgeX. EdgeX is an open source IoT platform that I work on, and within the EdgeX project, we use Redis for both persistence and for message communication. So our agenda for today, I want to first quickly talk about EdgeX and give a brief introduction. So we'll look at the architecture, explain some of the components, and it'll come quite evident where we use Redis, but mostly to put some names to some entities that we'll talk about later, so we're not completely disconnected. Next, I want to look at Redis and how we use it as a database. We have entities that we need to persist, and they have relationships, and the way we go about storing that is quite interesting, and we ran into a problem or two and have a little learning experience we'd like to share. Next, we'll talk about Redis Streams. This is something that we just added in our code base now and will be in our next release, which will be Geneva, and I'm quite excited about that. I'm going to talk about that and what I possibly think we could do going forward. And finally, just a conclusion and some final thoughts. So, what is EdgeX? So, a quick elevator pitch about EdgeX. So, EdgeX is an open source IoT platform. It allows you to manage all of your IoT devices and does a lot of the heavy lifting you would need to do for a complex system comprised of IoT devices. We have a lot of functionality, allows you to plug and play basically any device you want into the system and gives you functionality and easy ways to pull data out of the system and perform further processing. An example of a good use of EdgeX. So say you have a sensor, a temperature sensor, and a fan, and you want to pull a bunch of um, temperature readings from your temperature sensor, and after it gets to a certain threshold, you want to actuate a fan to turn it on, right? You can easily connect those two IoT devices to EdgeX, ingest the data, and then on the opposite side, pull that information out, perform some analytics on it, and then using the APIs of EdgeX, you can actually send that command down to the fan device. And it becomes a lot easier, and EdgeX does a lot of the heavy lifting because you don't need to know where that device is, the IP address, or any of that. EdgeX will handle that for you. So that's just a simple use case. It's a very powerful system. Go to the website, check out our code. It's a fun project and very, very awesome and powerful. So now that I give you 15 seconds and you've graduated EdgeX University, let's look at the overall architecture. So I know this is a bit complex for my little 15-second elevator pitch, but essentially this is the overall architecture. We're going to mainly focus on the middle section, those four horizontal areas there. So explaining how data comes in the system, and especially how it's going to be important to this talk. We're going to start from the bottom and then work our way up real quick, and I'll just define a few things here. So at the bottom, we refer to this as our southbound. Southbound is our IoT devices. These are our light bulbs, our fans, our temperature sensors, and these generate all the data. Next up, now within our EdgeX platform, we have device services. So our device services are components in the system that know how to talk to these IoT devices, or southbound sensors and devices. We provide an SDK here, so you can easily plug in and talk any type of communication with these devices. So say you have a sensor that talks Modbus, you can write something really quick that ingests that data and puts it into EdgeX, and you can leverage all the other functionality that we have. Next is core services. So information flows from the devices to device services, and it goes into core services. Right now we're talking about core data. Core data gets that information, persists it, and creates an event, and then sends it to the next two layers, and I'll kind of bundle these together. And the next two are supporting services and export services, and these are just ways to add additional functionality to your data processing flow. So say, for example, you want to add a rules engine to have really complex logic happening on events. So example, running tally of temperature readings, and if you reach a threshold for a certain amount of time, you want to actuate a fan, right? That you could use a rules engine for that and be very flexible and easy to do. So that's a very brief overview of the system. I think that gives us enough to kind of go forward and talk about how we use Redis for persistence, where you can kind of see we do that with core data, and that's where we're going to focus, and how we use Redis for a means of communication, which you can kind of guess it's the layers of core services talking to supporting services and export services. So dive into how we use Redis for persistence. So for simplicity's sake, we're just going to focus on these three entities. I think with the little brief overview I gave, these names kind of have a little bit of a meaning to them now, and you kind of assume what they do. So just quickly, a device is a IoT component. It generates the data. A reading is the data generated by a device. And an event is, I just say it's a change in state of the system. In our case, it's just going to be a temperature sensor grabbing the current temperature over a given time. So I guess the change in state is time, and we're just capturing that data. It's a little bit of a bad example, but these kind of fall into each other a little bit. So let's think about how these are associated. So just so we can kind of lay out the actual data and what it's comprised of. So if we start with device, which is simplest, it's just a construct with a bunch of naming identifiers, ID and name. And there's a bunch more that we won't even get into. Not useful for this talk. The next simplest would be reading. So a reading has its identifiers and obviously its value, which is the actual reading. So if we're talking about a temperature sensor, it would be 79 degrees. That would be the value. And it's associated with device, but it's associated with the string identifier, where the string of device is the ID of the device it's associated with. And the most complex, finally, is event. And like reading, it has an ID, and it's associated with device by the string that's the ID of the device. But this one is a little bit more complicated because it contains 0 or more readings, and this will get a little bit more interesting later when we talk about some roadblocks we ran into and how we got around that. So let's talk about how we organize the data. So when we think about persisting, I learned this at a Redis training session. So someone asked a question, I forget what it was, but I think it was something related with one of the Redis data structures, and the person giving the presentation said, if you stop and think about the way you need to access your data before you just put it into Redis, you'll be a lot more successful. So ever since I heard that, I've been kind of going with that philosophy, and I'm going to use that here because I think it helps tell the narrative of why we do some things and explains, and it kind of just naturally just flows. So as we're looking at these entities, and I'm only really going to focus on reading and event because you'll see the rest of the system just kind of follows the same pattern. So when we dive into how we're doing this and why we're doing it, I want to start with these questions because then it kind of just paints the picture. So first, look at how things are related, if there are any relationships. Then look at how we need to access it. How does the rest of the system need to retrieve the data? And then this will kind of tell what kind of Redis structures we should use, and then that naturally just tells you what commands you can use, and you just got to pick the best one, right? So start with reading. So first question, does it have any relationships? Yep, has one. Device, simple. Okay, cool. Let's keep that in the back of our minds. So next, let's think about how we need to access this data. So it's not completely obvious, but just going through the system and looking at how various components need to interact with readings, these are the ways that we need to access the readings. So we need to do it by ID. We need to be able to get all the readings in the system. We need to be able to get the readings given a certain creation time. We need to be able to get all the readings for a specified device and get readings by their user-friendly name. So given all this, what we do is we use this strategy. to persist. And that strategy is we take the key, so we create a key value pair. The key of that key value pair is the ID of the reading, and the value is the JSON representation of the reading. Now we've essentially persisted the reading. It's there, the data is there. The one part we're missing is the ability to access it by other identifiers. So you may have a key value, but how do you get all the readings out of the system, right? One can say, oh, you could just give me all the key value pairs and just dump them out. That doesn't work if you're doing this for other entities such as devices and, and events and whatnot. So, and the same goes to same goes for the situation where you need to obtain all the readings for a device. There's no easy way to do that. So what we do is we take all that other data and we organize it into sorted sets so that we can query later and get and list the information that we need, and then we can construct the right answer, I guess, answer, so to speak, right? So let's walk through this step by step to see how this works. And I want to go through each of the operations of create, read, update, and delete. And we'll do that for reading and then event. An event will be a little bit simpler because once you do it once, you kind of know what's going on here. So this is my crude drawing or crude representation of the two Redis data structures we use. So the rectangle up top is our key value store. I say store, but it's our key value area, which is going to contain our key and our value. And the rest of the bottom are circles, which represent sorted sets. And above them are their names. So the bottom two on the left, I just pre-populated with some junk data just to show that before we start adding anything, there could be many, many keys in here. And it's just, I guess, a nice way to show that there could be information in there. Okay, so pretend we want to walk through, so pretend we want to add a reading. So this is going to be the whole process for that. So first we do is we create that key value pair, like I said. We use a set command where the key is the ID, and I use ABC here just for simplicity, but it would be actually UUID, some long number with dashes in the middle and all that good stuff. But the value would be the JSON representation of that reading. So now, fully persisted, we have the data in the database, but we're missing those relationships and organizing the data in a way that we could pull it back later. So that's where these sorted sets come in. So now we would add that ID in the reading sorted set with the Z add command, and we use 0 for the score, which we could essentially just use a set, but nonetheless, we use this. This reading sorted set acts as the whole bucket, the bucket for all readings. So organizing the data in this fashion will allow us later to say, hey, we want all the readings. Just give me all the IDs in this sorted set reading, and there's all of our readings. And if you need to go further and get the actual information that are associated with those readings, you could just perform gets on those IDs and walk it backwards. But that's how this is going to start flowing. So then now that we added that ID into the reading sorted set, we add into the reading created sorted set, but instead of a 0 for the score, we're going to add the timestamp of when the reading was created. Now this will allow us, when we want to query the data, this is organized in a fashion where we can specify a time frame or range and kind of filter out the readings we're interested in. Now, the first two sorted sets were a little different than this and the next one. So the first two have keys associated with them that are essentially static. All right, reading is not changing. Reading colon created. So the colon is a way of name spacing, right? You could use anything, but colon is the idiomatic way of doing this. So, but this one, this sorted set, reading colon device colon fan, is what I'm going to call a dynamic key, because it's dependent on the information contained in the reading. So we created a reading. It has this device field and it's called fan. And so the device it's associated with is named fan. So now we need to create a sorted set reading colon device colon fan, which is comprised of the data. So it's dynamic in some sense. So we create that and we add the ID to that sorted set. And we do the same thing with with the name. So we essentially, these last two, dynamic based on the data that that houses the information. So you kind of have to do a little bit of programming magic here. Not really, but this will come back a little bit later. So just keep in mind that these last two are a little bit dynamic. So now we know how we add. Let's think about how we read. Well, we already thought about that because that kind of drove how we put the data in. So we get all the information out by kind of the opposite of the I'll call them put commands, but the add commands. So in Redis, you can actually look up like set, you'll automatically see it's related to get because it's basically the inverse. So basically use these inverse commands here. So for the ID, you just do a simple get and you have your reading. Just the information you put in there. It's the information for the reading and you're off to the races. But for the rest of these, you got to look up the IDs that are in those sorted sets and then look them up. And we do that with the zrev range, which gives you all the information, all the members of a sorted set, but in reverse order. And for creation time, it's a little different. We do z range by score, so it gives you the ability to limit the members you get back by giving a score. And remember, our score was a timestamp, so it works nicely how everything is organized by in incrementing order, and then you could just kind of filter the block you're interested in by supplying an upper limit or a lower limit or neither. So let's walk through an example of reading a device, reading a name, reading a reading. So all these terms get overloaded. So obtain a reading by device. So this is the most complex of the situation. So first you would have to take the name of the device you're interested in. In this case, it's fan. You would construct your dynamic key and you would get reading colon device colon fan. Now you can execute your zrev range, get all the IDs that are associated with that device, and now you have the ID. From there, issue a get command with the ID you retrieved, and now you have the JSON, which you can encode, you can unmarshal and do all that good stuff, but you essentially have the data you started out with. So you successfully read the data that you've put in there by the construct or the criteria you wanted to, right? And this works exactly the same for created reading, getting all the readings, and getting a reading by name. All these terms get overloaded, so hopefully I'm not losing you or saying the wrong things consistently. So now that we looked at the create, the read, now we need to look at updates. Updates are easy. Just delete the record. We haven't gone over deletes. We'll do that in a second. We'll walk through it. But you simply delete it like it doesn't, and treat it like it's never there, and just add it. So get rid of it and treat it like it's new. Take the new data, and that's the stuff you persist. So this is the easiest way to go through. So we've already walked through an add, so we know that portion of it. But let's walk through the delete to see how that portion works, because that's kind of how an update works. So for delete, deletes you can think of falls into one of two buckets. Either you have the ID and that's the ID you want to delete. In that case, just remove the key value pair, and that you can do that with an unlink command, and then use zrem to remove that ID from all the sorted sets that you added to, and then your data is clean. It's gone and deleted essentially. The other situation is if you have like a secondary association. So if you're trying to delete something by a name or a device, right? So it's two parts to that. So not only do you have to delete, you have to treat it like you deleted by ID, but first you have to get that ID. So you do that by a zrev range on the sorted set that you're targeting. You get all the IDs you're interested in, and then you perform the unlink and the zrem like we just mentioned with the ID. So I know it's a little complex, but we're going to walk through this right now to show what we do. So Again, targeting a reading by a device. I'm trying to go a little slower so I don't mess up any of the terms here. So given a device name, say we want to delete all the readings associated with it. What we do is construct that dynamic key, reading colon device colon fan, get all of the IDs associated with it. We actually read, do a get with that ID. So we actually read the data out. And this is actually important. It's not initially evident why we do this, but like I mentioned before, we have these dynamic keys of these sorted sets. So we need to construct these keys. And the only way to do it from an ID is to get the original data and to look at it and say, okay, its name is example, its device it's associated with is fan. Now we can construct those dynamic keys to remove them. So it's a little complicated. I shouldn't say complicated, it's a little not straightforward, but let's go through the example. So now that we have that information, we can do an unlink, excuse me, to remove the key value pair. Now the data is essentially deleted. And I want to point this out because, again, this will come up a little bit later, but because this doesn't exist anymore, it actually invalidates all the other linkages in the other sorted sets. Because pretend that a parallel process is running right now. Say we've executed this, Redis has removed this from its key value pair. The parallel process comes along and says, hey, give me all the readings for device fan. It's going to enter the sorted set, reading device fan. It's going to get ABC. It's going to perform a get on ABC, and it's going to come back with nothing, an empty result. The application is going to treat that, and this is application logic. The application is going to treat it like it doesn't exist. It's going to say, oh, nothing exists, empty, goodbye. So it's effectively deleted at this point, and that's kind of important. Well, it's not really important now, but again, we'll see this later, so just keep all this in the back of your mind. So now that we've removed the key value pair, now the rest is just cleanup. We're just removing the IDs from all the sorted sets that we use for basically organizational purposes or relationship purposes. So we remove it from all the readings, remove it from reading created. Now that we did our previous get, so we're able to construct this key, we remove it from there. And the same thing with name, we remove it from there. And we're good. Everything is removed. So that's how we deal with, well, that's how we interact with readings database. The next, I want to look at events. So events is very, very similar. It's a little bit different in some of the respects because it has the additional association to readings. So let's walk through that real quick. So let's go through thinking about events real quick. So relationships, okay, we have device like we had with reading, and we actually have readings. Good. Let's keep that in mind because we could just create sorted sets for those, retain the relationship and association, and we'll be good. Right now, let's think about the way we need to access this data because this kind of drives the way we store things. And because this is basically similar to readings, we just do like we did with readings. We just create a key value pair. The key is the ID, the value is the JSON representation, and the rest of them we could just put the ID in sorted sets, name them properly, and we can get them all back pretty easily with a few steps. Great. So we're not going to walk through this because we've done this for readings, and it's exactly the same. So to save time, let's just pretend the add functionality is the same way. Read, same way. If we look at this, it almost looks exactly like readings. It just has a few different constructs in here. Same thing. Go through and to get the data out, we just use the reverse commands. I call them reverse commands, but set is get, and putting something into a sorted set, getting it out of a sorted set. There's a few commands depending on the type of query you want or the type of data you want to limit. It is what it is. So that's how we read. Again, not going to walk through this because it's basically the same thing as reading. update is really the same as reading. So you just delete any existing record and then just add it with new data and treat it like it's new. But here's where it gets a little interesting. So deletes are the same, right? So just remove the key value pair, remove from the sorted sets for the association relationships. Great. We don't need to go through that. But the layout's a little different, obviously, because down the right is the most important. So we have more sorted sets here, and for readings we had 4. Here we have 6. So this is going to take a little bit more processing to get rid of, because we have 2 more, and we have to issue 2 more commands. Excuse me. But the sorted set in the right is going to be interesting how we have to deal with this really for deletes. So I know we skipped over deletes because initially in our implementation, we deleted the same way we deleted readings. And this led into a little bit of a performance issue. And it wasn't a performance issue on Redis part. It was a performance issue on the application. Now we were doing all this heavy processing inside of the application and not in Redis. So think about as the data grows and you need to do something like a delete and how many steps it takes and how it can get really slow, especially because when you have something something like an event that has many readings, and a device can have many events. So when you get into a situation where you have a device that has, say, just for simple numbers to show how this grows exponentially, if each event has 10 readings and a device has 10 events, you have essentially 2 nested for loops. I think I alluded to this earlier. So you have to iterate over each of the events, and for each event you have to iterate over each of the readings and perform these 4 or 6, well, it's actually 4 or 6 cleanup processes for the assorted sets that we've constructed just to retain the organization and relationships. So this grows almost exponentially, and one of our black box tests, or actually our performance engineers was running this, and so it's really slow, and it's taking more than, I don't know, a few seconds, and our tests are failing. So what we did was we used a divide and conquer approach, and we really leveraged the fact that, like I mentioned earlier, that when you delete a key, it's essentially deleted, right? You have some other cleanup you need to do to prevent a memory leak, but it's essentially deleted. So what we did was we split this into 2 parts. What we did was when we do a delete, we simply rename the key. We prefix it with something, and then we kick off a background process to later clean up, not much later, like in milliseconds later, and just take that longer initiative to clean up the data at another time. This allows us to respond to the user, okay, thinking about a REST protocol. Hey, delete all of my events really quickly. Say yes, yeah, delete it. Not really. It's deleted effectively. Like you go do a get or you try to recreate that, it'll be fine. But we could do the long-term processing in the background, and we don't have a performance hit for that. So just to illustrate this, so using the rename command is how we achieve this. So we use a rename command on an existing event. So pretend an event exists called with the ID of DEF for simplicity's sake, and it has linkages in all of these sorted sets except bottom right, because that bottom right one is for DEF event that contains the reading, so it won't contain itself. But this has 5 different linkages that I would have to go through and iterate on to remove. Instead of doing that, so in the situation I'm referring to, it's deleting events by device. So instead of constructing the device key for the sorted set, instead of constructing the key for the sorted set that's comprised of the device name and then performing a get to get the actual JSON data, and then being able to clean it up, with all the other dynamic keys that are out there. Instead of doing that, we just do a simple rename, which is really quick. Rename, and it's effectively deleted, and move on. And it invalidates everything else. Because I think I said this earlier, but if something comes along and says, give me all the events for device fan, it's going to get DEF, but then it's going to try to do a get command. It's going to come back empty, and the application is going to say, nope, this doesn't exist, and it's pretty much deleted. And this works pretty well. And you can actually do the same thing for readings, and we do. So doing this, we ended up with some faster response time. So problem went away. QA performance engineers were happy. It's fine. And this was the result of that. I apologize because I actually was the one who worked on this. I didn't capture, or at least it's lost. This was a issue from a while ago. The original benchmark from before the fix doesn't exist. And these benchmarks were something I used to communicate to the rest of the community how effective this process was. And we accepted it, so this was okay. But this is the metrics that I published in the original issue. We can see that if you go down to the million readings situation. I only focus on readings here because I wanted to make it simpler. Instead of doing say 100 events with 100 readings each, simulating X amount of commands, you could just do the same with just readings. It's not the same, but it's pretty close, and it's an easy way to do this. But that's the approach I took back then, and I know a little bit more now and probably would do it a little bit differently, but this is what we did. And you can see that for a process that would probably take roughly 28 seconds, if you combine the renaming time and the background process, right? Just say they're about the same. The user gets back a response in 1.29 seconds, and the rest of the processing gets pushed all the way in the back end. So you can't compare this to what the problematic code did, but this becomes interesting because we tried this another way. And we tried doing this using a Lua script. And the approach we did was we took that same functionality, serialization and all, because when you do the get command, you actually have to get the JSON and you have to inspect it. All that, all in the Lua script. And we uploaded it to Redis. And like a stored procedure, like you would do in another SQL and other SQL-esque databases. And then we just simply executed the script. And this is how long it took to completely erase everything. So see, for just looking at the most extreme case, because that's the easiest, million readings took 14.55 seconds relative to the combined 28 and probably half, 28 and a half seconds it took to do the divide and conquer method. So it was extremely faster to just put in the Lua script and upload it and to just constantly just hammer it. We didn't go with this approach, and at the time it wasn't due to any issues or anything on the part of Redis. It was a maintenance concern. We didn't have, or we still don't have, many contributors to the project that write Lua. So I willing to bet if I could have found the Lua script I used here, it would have probably been very bad. So you were protected. Your eyes are protected from my bad Lua. So that's basically how we use Redis for persistence. We have about 15 other data structures that require persistence, and they all follow the same strategy. We do the same thing. We maintain relationships with sorted sets, and we use the same pattern. I think events and readings were the most intriguing because we actually ran into that problem, and it's a simple use case that you don't really have to dive too much into EdgeX to actually understand what's going on. So next I'm going to talk about Redis Streams. And picking up where we left off on events, right? So flowing through the system, let's talk about when core data gets an event, and in this case it's persisted, and what does it do next? Well, it sends that event on the message bus. And what that means is it actually communicates that event to the supporting services and export services. And I highlighted this in yellow, but mostly we're going to talk about the the top right additional services, because to me this represents what the application services, and I'll get into what that is in a second. But I think in the future we're going to leverage this more for a rules engine so that we can really get data out easily from core data and just into other systems for a lot of flexibility. So we have an existing rules engine, but we're looking at replacing that with something a little better, quicker, and lighter, and all the good stuff. So I think we're looking at connecting that on our message bus. So a little about the message bus. Our message bus is a standalone module in our system that provides publish and subscribe functionality. It's abstracted over whatever the underlying mechanism is. So right now we have it for ZeroMQ and MQTT, and most recently Redis Streams. This is a common module that's used in other components. So core data uses it, application services uses it, and then if we decide to put this into something like a rules engine, a rules engine will use it. And any component that wants to be able to pull data off of the message bus can do so. So application service, I know I said this a couple times just to talk about what it actually is. So an application service is a component of the system that I'll say pulls or reacts to data that are processed by core data. So event comes in and you want to do something with that event, that's an application service. An application service is built using, or can be built, because you could build this from scratch, but why would you? You can build this using our App Functions SDK, and this provides a lot of functionality to easily receive data off the message bus and do some processing of that data. So you can pull in data, and I know my earlier example was pull in data, filter out the events that you're actually interested in, compress them, and then send them up to whatever cloud instance you have for a long-term storage or ML processing and your ML flow and all that good stuff. So it's a good way to integrate in the system. So you see that we have the device services SDK is a good way to start getting data into the system, and application service is a good way to get data out of the system. With the two, you can do a lot of good things. So how are we using Redis Streams? So I know that we talked about the abstraction layer for how we talk to EdgeX. Let's look more deeply at the Redis side of things. So we have publishers and we have subscribers. They're basically the same thing from the point of view of the message bus and people that use it, because both features are available to whatever consumer. But pretend we have both opposite ends. So publishers are the ones who are adding entries to a stream, and we refer to it as topics because it's an abstraction that doesn't care what it's called under the covers. And subscribers read the latest entries from a stream. And we do this with the commands xadd for publishing and xread for reading. Now, this is our first iteration with Redis Streams. So this is a real publish subscribe type of mechanism, right? So let's look at how we do this, because I love just crude representations of everything. But I like this because it'll show what commands we're actually using without just throwing commands on the screen. So first, let's think about how our subscriber can communicate that he's interested in the message. So our implementation uses the xread command, but we supply the block 0 command argument to tell it, hey, we want to block indefinitely until a message comes in. And we also provide the $sign identifier, which tells Redis we only want messages or entries in the stream that have entered after I've executed this xread command. So essentially, if the publisher pushes a bunch of entries into the events stream, this subscriber wouldn't get it. He'd only start to get entries after he has executed his xread command. Well, just some holes in that, but this is our first naive implementation, and we're gonna iterate over this and add some more functionality. But in this case, our publisher, using the xadd command, adds an event to the event stream. Now we use the asterisk here as an identifier to tell Redis, you create the ID for us. It's because Redis is great at managing the IDs and keeping them all in order and whatnot. So let Redis do the hard stuff. At this point, the message was added to the event stream and makes it all the way back to the subscriber. It's a very, very simple use case, but we can do more. And when I was working on this, I was actually really excited looking at the other functionality that Redis Streams provides, mostly consumer groups. And this would be the next step that I would like to take with this implementation within EdgeX, would be add functionality for consumer groups. And this would be rather easy because publish functionality would be exactly the same. You would still publish with an xadd and you're good. Subscribe functionality, though, would be a little bit more different because you would not only need to read with a different command, x group read, and then there's other arguments, but whatever, that's fine to add. But you would also have to add group management functionality. So if you want to create a consumer, it has to be in a group. If that group isn't created, you have to go and create it. And if the client, in this case, subscriber, goes offline, shuts down, exits, whatever, you should clean up his subscription or his membership to that group. So that way things work out very well. So there's some group management functionality that we would have to add. And finally, I think this is a little bit harder, but adding functionality for hacking of messages. So our abstraction doesn't allow for this, so existing clients won't even know how to do this because they've just been working with publish, subscribe. They don't know the idea of subscribe for a message and I process it and then hack it. But this would be really good to add because it would allow for fault tolerance, right? So adding consumer groups will allow you to scale out. So you could take application services and you can have multiple application services that do the same thing, but basically scale them out. You can't do that now because everything's publish, just a broadcast message. So if I have 4 application services that all compress and send to my cloud instance for long-term storage, I'm gonna have duplicates. All right, the event's gonna come out, get put on the message bus, and both of them will get it processed and send it up in duplicate. Consumer groups, that won't happen. It'll actually be load balanced so that your processing is actually best utilized and you won't have duplicate messages. You can also do this with a rules engine if you have a lot of processing and you need to really scale out. The other side of this which is hacking, would prevent against lost messages. So Redis Streams allows you to have a consumer group. You have a client ID or consumer ID, and you consume messages. And when you're done processing a message, you acknowledge it, right? So when you pull a message, it gets put into a pending list. When you are done processing, you acknowledge and it gets removed from the pending list, and it's done. Now, this allows you, when I say protection against lost messages, if I pull a message from a stream and it's in my possession and my process dies, then the message is lost, right? Normally, it would be lost. Now, when I start back up, I can say, hey, I'm client ID, whatever, Anthony. Give me my pending messages because I was in the middle of something. I don't remember what it was. Gets your pending messages, reprocesses them, and then acknowledges them. So you won't lose a message, right? And this allows for great quality of service of your messages. You can actually, depending on your implementation, it's not a Redis thing. So Redis provides the capability of doing this, but we would be able to provide a guarantee. Either that guarantee be everything gets processed at least once, or you can really hone in on how you act messages and really solidify that and say, we provide an exactly once guarantee, which would be awesome. That'd be great functionality to have. So I'm excited for where we can go. The opportunity is there, and we'll see where we go. So that is how we are using not only Redis Streams, but Redis for persistence. I think this was all, hopefully this is all really informative and made some sense. But before I go on, just a few thoughts. Well, not really thoughts, but I thought this would be cool to share some metrics. So a little bit about EdgeX. So EdgeX, we up until this point have been supporting two databases. We've been supporting Mongo and Redis, and Mongo has been our default implementation for a while. With this release, the Geneva release, we are going with Redis as our default implementation and deprecating Mongo functionality. So it goes to show how much we love Redis and how well it's working for us. Being an IoT device platform, an IoT platform, I'm sorry. A couple of the metrics I'm going to share are very important to us. So like startup time, image size, speed, very important to us. So Redis helps with all these things, and we'll look at the stats in a second. But just one thing about these statistics. So the statistics I grabbed are from our performance engineers, and they're from 2 releases ago. So our Edinburgh release. The reason I had to go back 2 releases was because our last release is performance metrics. It didn't include Mongo, so it's kind of unfair battle there. But here's a fair fight between the two. So we can see by using Redis here, we got 24-second faster startup, which is amazing in the IoT world because 24 seconds means you just lost a bunch of data. If IoT devices are out there and just sucking up data, you just lost a bunch, which is amazing. So our resource usage at startup. So we save about 36 megabytes and 2% of CPU usage. This is kind of shocking to me, but a system that's not being used is kind of a lot. Another very important one to us is image footprint. So we save about 330 megabytes over overall footprint by going to Redis. This is amazing. And a really cool one is event processing performance. So here we save about 26 milliseconds. Just quick on how this is determined. So when an event is created, it's time-stamped. Not event, I'm sorry. When a reading is created, it's time-stamped. It's actually the event, I apologize. So when a reading is created, it's pushed up to device services. Device services then creates the event, which is time-stamped, sends it to core data. Core data persists it, sends it to message bus, and then on the message bus gets ingested by application services. Application services then sends a request to core data and says, mark this event as pushed. So that time difference between when the event was created by application services and when core data marked it as pushed is the difference there. And so you could tell how fast something ran through the whole system. So that's it for me. I had a lot of fun with Redis. I learned a lot. It's a great tool, great tools to work with, the CLI and all that good stuff. It's amazing. It's really fun to work with something and then see the benefit of all the performance right away. So it's been a pleasure. Before I go, I just want to give a quick shout out and thank you, Dell, my employer. Thank you for giving me the chance to give this presentation and to work on EdgeX for the EdgeX community. Thank you for being awesome. You're amazing, fun to work with, great group of people. And for Redis Labs for allowing me to give this presentation. Please do yourself a favor, go to the edgexfoundry.org. Please look, review, and verify everything I said because I'm crazy. So go there, join the Slack channel. They're amazing people, great community, fun project. Jump in and help if you want. With that, my last thank you is to you for your time and attention, and I really hope you enjoyed this presentation and found it helpful. Enjoy the rest of the conference.